So maybe this one's the last one, but we're going to go over some different types of integrals that you should know how to do, basically. So first let's talk about the mean value theorem for integrals. So if you don't remember, mean value theorem was like the it's up here. It's like the average rate of change between 2 points is equal to some derivative tangent line at a point C. So we have the mean value theorem, but for integrals. Okay. So what this one is talking about is the average value of a function. That's what this is. It calculates the average value of a function. So whenever you see average value of something, you're probably going to be doing this. So you'd notate it by saying f_av for f average, and it's equal to 1 over b minus a, integral from a to b of your function. So pretty straightforward. That's average value. Whenever they ask for average value, just know 1 over b minus a, and then your integral. So all you have to remember is this 1 over b minus a part. Okay, now let's do I'm not going to go over volume, like you know how you have a graph and it like rotates around a point, like around here, and then your shape ends up like this, and you've got like slices of it that you add up. I'm not going to go over that because Mr. Palmer said it's not as common in BC as it is in AB, so let's go over some more important integral stuff. First thing would be integration by parts. So I'm going to label this or title this integration techniques. Let's write it in blue, because this is a pretty big concept. There's a lot of integration techniques. So the first one would be by parts. Integration by parts. So essentially what you're doing is, it's kind of like the product rule for integration. So if we have an integral with like x sine x dx, we don't know how to integrate this because we can't u sub this and have it equal this x, and we can't u sub this and have it equal sine x. So what do we do? So that's where the integration by parts comes in. So the formula for this, I should have written that first. Let's move this down here. The formula for integration by parts is this: integral of u dv equals to u v minus integral of v du. Okay, I'm gonna try my best to keep my v's and u's very distinct from each other. So essentially, you're going to take the derivative. You're gonna make one u, and you're gonna make one the derivative of itself. And this is just the, okay, you know what, let's do the problem and then you'll see. We'll do a few. Let's move that here. Okay, so this is our problem. So the u that we want to choose, or the one that we want to choose to differentiate, has to be the one that is not cyclical. So well, it has to be the one that we know the derivative of at the very least. Yeah, and generally you want it to be the one that isn't going to just go back and forth between derivatives. So like sine of x, it's either sine x or cosine x, and sometimes there's like a negative sine x, negative cosine x, but generally it doesn't go beyond the sine and cosine. But if you have x, you take the derivative, it becomes 1, and then you take the derivative again, and it becomes 0, and then it just stays 0. So we want our u to be x, and we want our dv, this part, to be the sine x dx. So this part is our u, and then this part is our dv. You see how that matches this here? So that's what we're doing. We're just relabeling. And our u is the one that we're going to take the derivative of, and our dv is the one we're going to take the integral of. So the derivative of u is du, derivative of x is dx. The integral of v, dv is v. The integral of sine x is negative cosine x. Because if you take the derivative of this, you get sine x. Okay, cool. So now we just have to follow this format. We just plug everything into there. So the way I remember it is you pair these together, and then you pair the new things together. So the single letters, just the u's, like not dv, du, but just u and v, and then the new stuff that you just solve for. So we're going to write this equals, and then uv, negative x cosine x. So I just put this negative 1 factor right there in front of this x so it looks better. And then our integral v, I'm going to move this negative 1 into the front, so this actually becomes plus integral of cosine x, and then our du, which is dx. So that is that integral. And then we can see here, we know the integral of cosine x, so this makes it really easy now, and we can get our actual answer without any more integrals. So the integral of cosine, so derivative of what is cosine? Derivative of sine is cosine. And then we need our plus c. Yeah, so that is how you do the integration by parts. Now let's take a look at another question similar to this. So I said that you want to have the one that isn't cyclical as your u, so you can take the derivative of it. But what happens when both of them are cyclical? So let's say I have an e to the x sine x dx. So now you can see e to the x, no matter what you take the derivative, it's always going to be e to the x. And then sine of x, no matter what, it's always going to rotate between sine, cosine, and like negative sine, negative cosine. So what do we do from here? Well, we're going to first just set u equal to e to the x. So just like, basically we're just seeing what would happen if it equaled to e to the x. And then the dv is going to be the rest, so sine x dx. So when we take the derivative of this, obviously we get e to the x, and then we have their dx. And then when we take the derivative, or we integrate v, derivative of what is sine? Negative cosine x. And then we fill in our thing here, just seeing what happens. So we have uv, negative e to the x cosine x, minus integral of v du. So this minus, I'm going to move in front of the integral, so it becomes a positive, and then cosine e to the x dx. I'm going to switch these because it makes more sense, because now it looks like, oh, I forgot the x after cosine, but e to the x cosine x dx. Okay, and then we have another integration by parts, so let's just do it one more time. So I'm actually going to move this So let's do it again. Set our u equal to e to the x, and our du becomes e to the x dx. And then we have our dv equaling the rest, which is this cosine x dx. The integral of that, derivative of sine is cosine. So now we just fill it in again. So negative e to the x cosine x, that stays the same. And then we have our uv, so sine e to the x sine x, minus the integral of v du. So we have sine x, wait, I'm going to write e to the x first, and then sine x, and then our dx from right there. Okay, so do you see how we have this e to sine x dx right here? And you see what we're looking for? We're looking for the integral of e to sine x dx. And that's right there. So all we're going to do is we're going to move this to the other side of the equation. It's like cheating, honestly. It feels like cheating. Because remember, this is technically like in front of here. So all these things are equal. All of this is equal to this. Like this is equal to this. We just didn't write it. That's why the equal sign is right there. It's like insinuating that we write it there. So if I add this to both sides, aka I'm moving it over here, then I'm going to have this e to the x sine x dx and this e to the x sine x dx. So that means I have two of them. So I'm going to write that. I have 2 integral e to the x sine x dx. Okay? So there's an invisible one of these in front of both of these expressions. And I'm only rewriting it now because I wanted to move this over here. And now what do I have left on the other side? I have negative e to the x cosine x, and then the positive e to the x sine x. So that's this stuff right there. And then all I need to do is divide by 2. And then what am I left with? E to the x sine x dx, which is what I'm looking for. That's what I'm looking for right there. And what is the answer? Well, it's negative e to the x cosine x plus e to the x sine x, just divided by this 2 right here. And that is literally our answer. This right here. We're looking for, what is this equal to? Well, this is equal to this. You see how these two are the same things here? So it feels kind of like cheating, but yeah, that is literally the answer right there. Oh, wait. Plus c, plus c, plus c. I can't forget my plus c. Oh my gosh. So that's integration by parts. Now there's another way of doing integration by parts that is much more convenient, and you use this way if you have one cyclical like derivative. So if you have like a cosine there, or a sine there, or an e to the x there, in like this spot, multiplied to something else, then you can use this di method. And it's called di method because the d stands for derivative and the I stands for integration. Like here, how we take the derivative and here we integrate it. And but this is also called tabular integration. So I'm going to write di/tabular. So this is still part of like by parts. So I guess I won't underline it. So this is still part of the integration by parts, but it's just a different technique of integration by parts. So let's see. So the format it follows is you have an integral of some x to some power, and then there's either now I can't remember specifically, but there's either like a cosine here, or it can be, actually, why don't I just write like blank, and then it can either be cosine or sine or e to the x, something that's like cyclical. Yeah, I don't think I wrote down exactly what, but basically this kind of thing. And then it's x to some power. So let's do an example. Let's say we have actually, I really like this technique, by the way. This is like, I don't know, I just find it really fun to do. Let's say we have this. So it follows this format here because we have this cyclical sine x, and then we have x to a power. So now what we're going to do is we're going to make a column that's labeled D and a column that's labeled I. So this stands for derivatives and this stands for integration. So we're going to integrate the one that's cyclical, and then we're going to take the derivative of the x to the whatever power, because this will eventually equal 0, but this will keep on spinning around and around. So we want to take the derivative of the one that will eventually settle down to a constant number. So I'm just going to write x cubed there and then sine x there. Can you guess what we're going to do? In the derivative column, you're going to take the derivative. So derivative of, and you're going to take the derivative until you get to 0. So derivative of x cubed is 3x squared. Derivative of that is 6x. Derivative of that is 6. Derivative of that is 0. So now we're at 0, so we can stop. And then you're just going to do integrate sine as many times until you get to where you ended up stopping your differentiation. So integral of sine x is cosine x negative cosine x. Integral of negative cosine x is negative sine x. Take the derivative, yeah. And then integral of negative sine x is cosine x. And integral of cosine x is derivative of what is cosine? Sine. Okay, and then all you're going to do is you're going to cross these diagonally and down one, like that. Until you touch the bottom integral. So this one, not going to connect to anything. This one's not going to connect to anything. And then another thing is that these values over here have a sign to them. So it starts off positive, and then negative, and then positive, and then negative, and then positive. So I normally don't write the positives, but I'll just keep them there for visualization's sake. So that's how you do DI method. So always remember, you start with you start with a positive number, and then you change a sign, negative, positive, negative, positive. You're just alternating. And these lines go down, like diagonally down one. And then all you're doing is you're putting these together, and you're just adding all those together. Like whichever one is connected with the line. So the answer for this equals. So first we have this positive x cubed and the negative cosine x. So that means we're going to have a negative x cubed cosine x. And then we have this negative 3x squared and a negative sine x. So that's a positive 3x squared sine x. Oh wait, I should have got rid of that thing first. So positive 3x squared sine x. And then we have a positive 6x and a positive cosine x. So that's positive 6x cosine x. And then a negative 6 and a positive sine. So that's, let me move this over a little bit. So that's a positive 6 sine x. And there we go. That is our integral of this. So that's a DI method. It's very clean, very cute. I love this. Yeah, I love it. Okay, next one we're going to do integration by partial fractions. Or should I make it just a different video for that? I'll put it in a different video so we can break it up a little bit. Next up, integration by partial fractions.